Okay, in this video, what we're going to look at is we're going to look at the different theorems or theorems that we have that center themselves around zeros of polynomial functions. Okay, so if you remember, a zero is one of the things that would lead you to a solution. Zeros, we're talking about your x-intercepts, or the places where you're crossing that x-axis. So the first one we're going to look at, or the big one we're looking at, is the fundamental theorem of algebra. And the fundamental theorem essentially says that each and every polynomial function with a degree of n has at least one zero in your complex system. So when we're talking about a complex number system, we're talking about a form like this, where each one of these parentheses represents a zero. Okay, so if you're looking at this c value, this is going to be the location at which you're crossing that x-axis. Now we do have some different types of zeros here. Okay, first we have real coefficients. Now remember, when we're talking about real, we are talking about any number, positive or negative. Now with that, we could have complex numbers. Remember, complex deals with the imaginary. If you have a complex as a zero, you need to always remember they come in pairs. In other words, if you have the positive a plus bi, then you automatically know your second zero has to be the negative. They always come in pairs. And that's the same when we're dealing with radicals. If we have a radical as a zero, and say in this case it's positive, well then we know the other zero is going to be the negative. So a minus c square root of b. Okay, they again always come in pairs, okay, as the plus and minus. So let's take a look at an example here and look at one way that you could see this theorem in action. So the question says to find a polynomial function with these stated properties. First, it's a third degree. It has only real coefficients. We know that we have 5 plus I and negative 1 are two of the zeros, and the y-intercept is negative 52. So the first thing we need to do is we need to, I would say, take a few notes. So those would be that we know your degree says that n equals 3. In terms of the zeros, we have 5 plus I and negative 1. Now, because this is imaginary, we automatically know we have the other zero, which has to be the minus 5 minus I. Because remember, they go in pairs. Since my degree is 3, 3 says I should have 3 zeros. 1, 2, 3. There we go. Now the other thing that we know is that I have a y-intercept. So in this case, we know that my b value is going to be the point 0, negative 52. So we actually want to find the polynomial function, and to do that says that your p of x has to be your 3 zeros multiplied together. So the first thing we know is we're going to have x minus the first c. Then we're going to have x minus the second c, and then we have x minus the third. So we have to figure out c1, 2, and 3, and we get those from our zeros. Okay. So for my first zero, we have that x is equal to 5 plus I. In order to turn it back into its factored form, I have to take all of this and move it to the other side of my equal sign. So this means we're going to end up with x minus 5 minus I equals 0. We have to do the same for the second, so x equals 5 minus I. Again, we're going to move everything over, so we're going to move this over. So we end up with x minus 5 plus I equals 0. And then the last one we have was x equals negative 1. So again, we're going to move it to the other side of my equal sign, so we end up with x plus 1 equals 0. So if we look at them, this is going to be the same as C1, this would be C2, and this would be C3 essentially. So we need to simply plug it in. So my function is going to be x minus 5 minus I times x minus 5 plus I times x plus 1. Now, in order to find your polynomial, what you need to do is you have to multiply them together. So this is where you make a choice. You either multiply your complexes together and then multiply the third, or however you feel like doing it is up to you. It just has to be done. For me, I would first work on my complex terms because they are the more complex idea, and you want to try and simplify things down as far as possible. So you're going to take one parenthesis into the other, so that's going to be x times x, so here you're going to get x squared, and then x times negative 5, so negative 5x, plus xi. Move to the second one, you're going to have a negative 5x plus 25 minus 5i. Move to the third, you're going to have a negative xi, you're going to have plus 5i, and we're going to have minus I squared. So in looking at these, there's a few things that we can erase right off the bat. And so when you look, notice I have a xi and minus xi, so these can go away. And then I have a negative 5i and a 5i, so those can go away. So here I have x squared. I have minus 5x is a minus 10x. I have plus 25. And then over here, notice I have an I squared. So you need to remember your rule, which says that I squared equals negative 1. So here this is minus a negative, so this becomes plus 1. So the whole thing becomes x squared minus a 10x plus 26. And we still have to multiply this by x plus 1. Okay? Now, notice my i's have all gone away, which is what I was hoping for, because a polynomial should not have any imaginary numbers. So now here we have to multiply again. So x times x is going to give you x cubed. X and 10x is a negative 10x squared plus a 26x, and then we're going to multiply with the 1. So this will be plus x squared minus a 10x plus 26. So now we need to combine. So all I have is an x cubed. I have negative 10x squared plus an x squared is a negative 9x squared. I have 26x minus 10x is a plus 16x, and then I have plus 26. So this is your polynomial. However, there's one piece we have not used yet, which is the y-intercept. So the y-intercept essentially says that we also have this negative 52 on the end. So we need to combine my terms together in order to utilize that negative 52 because it is your y-intercept value. Okay. So here you're going to end up with x cubed minus your 9x squared plus your 16x, and then combine. So we have 26 minus 52 is going to give you a negative 26. And this is going to be your polynomial function. Alright, let's work another one. So here I have fifth degree. I have that 1 is a 0 of multiplicity 4 and negative 2 is the only other 0. So again, when we're talking about your degree, we are talking about n equals 5. And then when we're talking about zeros, we have 1, but we also have that it occurs 4 times. And then we have negative 2, which is going to occur once. So if you look, here's 4 zeros, and here's one more. I have them all. Now the last thing I have is that I have a leading coefficient, and in this case it is 4. So the first thing we need to do is we need to write out our stuff. So here we have that p of x is going to be x minus 1 to the 4th power times x plus 2. So how did I come up with that? Well, remember, when we have a 0, we're saying that x equals that value. To turn it into a 0 simply says we need to go backwards. So here we're going to have x minus 1 equals 0. Again, the same. We have x equals negative 2. We need to turn it backwards, so x plus 2 equals 0. Okay. So now we need to multiply all of this out. So you're going to essentially do a lot of foiling. So remember, when you have to the 4th power, that is the same as looking at x minus 1 times x minus 1 times x minus 1 times x minus 1 times the x plus 2. So what I would do is I would multiply these together through FOIL. Then I would multiply these together through FOIL. Then I would multiply them together, and then I would pull in that x plus 2. Okay. Once you do that, you should end up with x to the 5th minus 2x to the 4th minus 2x cubed plus 8x squared minus 7x plus 2. Now the last thing we need to take into account is the fact that this leading coefficient here is supposed to be 4. So that means we have to do 4 times your p of x. So we're going to put a 4 on the outside of your whole polynomial. And with that, we then have to distribute that 4 through. And so once we do that, we end up with our polynomial being 4x to the 5th minus 8x to the 4th minus an 8x cubed plus 32x squared minus a 28x plus 8. And if you look at this polynomial, what you'll be able to see is that everything holds true. First of all, it has a degree of 5, and its leading coefficient is a 4. We used 4 zeros of 1 and 1 0 of negative 2. Multiply that all together. Alright, let's look at another. So here we need to find the other zeros given the polynomial and at least one of the zeros. So what you need to look at in this case is that when we're talking about at least one of the zeros, that would be this value over here. And the polynomial function is everything in front of it. Well, one of the things that we know is that the degree tells you how many zeros you need. So here, this is a degree of 4. So what that actually means is that we should have 4 zeros at least, okay, or 4 zeros. Now, this I here tells you that automatically you know it needs to have its pair. So when we're talking about zeros, right now we know of negative I, we also know positive I. So there's 2 of them missing. So the first thing that I would do is you could look at your P's and Q's, and so to do that says that you're going to be looking at your last term and the coefficient of your first term. And so we're going to go ahead and then be able to state them. Now what this is going to do, again, if you remember, is that this is going to give you a pool that you can work with. So when we're talking about P, we're talking about factors of 6. And when we're talking about Q, we're talking about factors of 1. And so here, my P over Q is going to end up being plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So I have all of these choices, or all of these are possible factors that could be used in order to find zeros of this term. So the first thing I'm going to look at is the fact that I have a 6 on the back end here. And so one of the things that I'm going to start with is I'm going to look at 2 or 3. Now the reason I'm looking at 2 or 3 is because I know if I'm working with 1, chances are that's not going to work because I have all these 5s and 7s. So what I want to do is I want to see if by chance using one of these middle zeros will give me what I want. Now the other thing I'm going to look at is the fact that my last term is positive, that my signs go every other, and so I'm going to go ahead and assume that a positive 2 might be what I need. So I'm going to use synthetic division, so that means pull the coefficients of your terms, 1, negative 5, 7, negative 5, and 6, 4, 3, 2, 1, 0, 4, 3, 2, 1, 0. You're counting your powers down. And then synthetic again says you bring down your first term, and then you take the bottom times the box goes underneath the next term. So 2 times 1 is 2, and then you add them together. So negative 5 plus 2 is a negative 3. 2 times 3 is a negative 6, and we're going to add them together, gives you 1. Again, repeat. 2 times 1 is a 2, add them together, and you get a negative 3. 3 times 2 is the negative 6, add them together, and you get a 0. This is what we were looking for. Therefore, we know that x minus 2 is going to be one of the zeros, or one of the factors. Now with this, I can pick up right here where I left off, so I'm going to go ahead and draw another box, and notice these have 3's in it, so I'm going to go ahead and use 3. Now usually the rule that you want to follow is that once you find a 0, test again to see if you have a multiplicity, but in this case, because these are 3's, I'm going to go ahead and skip that, assuming that my 3 should work here. So 1 times 3 is 3. When I add this together, I get 0. 0 times 3 is 0. Add them together gives me 1. 1 times 3 is 3. Add them together gives me 0. So definitely worked, which means I know x minus 3 is going to be another factor. Now, what does this leave me with? This leaves me here with, this was x to the fourth, x third, this is x squared. So this is going to be x squared plus 1 equals 0. And so if you look at this, if we were to solve this quadratic, I hope you see now where we get negative I and I. So in this case, if we solve the quadratic, you would end up with x squared equals negative 1. Take the square root, x equals plus or minus the square root of negative 1. The negative here pulls out as your I term. Square root of 1 is 1, so x is plus or minus I. Well, in this case, all we were looking for was the zeros. So what we have is that all other zeros are the following: plus I, 2, and 3. Furthermore, all have a multiplicity of 1. Alright, so if you have any other questions, please let me know. Otherwise, that should get you started in looking at theorems of zeros using polynomial functions.